All right, we're back for some more discussion about chapter 2 and orbitals and their shapes. Well, orbitals have shapes. We've alluded to part of that, and let's talk about it some more. There's a different characteristic shape for each of those orbitals. S, P, D, and F have shapes, and they're derived by the calculated probability areas that come from the Schrödinger equation. And each one of those orbitals gets a probability shape determined by those quantum numbers, those n, l, and m sub l values. And so each of these orbitals has shapes that make some kind of sense to a point. So let's think about it a little bit more. The 1s subshell has a spherical shape, and on the inside of it is a region of lesser density for lesser probability for electrons, because that's where the nucleus is. And so there's a spherical surface, and there's a very low probability of electrons in the very middle. The 2s orbitals, the 2s orbital is the same shape, but inside of it, it has a spherical space, a spherical surface of 0 electron probability. That's a node. In other words, the different colors in this diagram, the red and blue colors, are representing two different signs of the wave functions, like different phases of a wave. We'll talk about waves again in a minute. And so there are some places that are nodes, and the nodes are places where there's absolutely no probability for the electrons to occur. So the 0 probability spot is the node. The 0 electron probability spot is right here at the end of that dot. And so the 2s has two levels that are possible for the electron to occur. The third, or 3s orbital, has within it two nodes of 0 probability where the electrons really aren't going to occur. And so there's like 3 concentric spheres around the nucleus for these the 3s subshell. The node then is a surface of 0 electron probability. There are places where likely and unlikely for electrons to occur. But the s orbitals are spherical, and they're the ones that penetrate closest and closer to the nucleus. So talk about nodes again. When we think about waves, we can draw these diagrams, and if you can imagine, this looks like somebody's got a jump rope fastened to the wall and they're wiggling it fast up and down. And the nodes are the places where there is no particular amplitude. As you create a standing wave, if you fix the rope on one end and vibrate it vigorously, you get a standing wave, and the nodes are the 0 amplitude places. So there are nodes in the probability spaces for electrons in orbitals as well. And so the wave has positive and negative amplitudes separated by 0 amplitude regions called nodes. So the plus side is above the 0, and the minus side is below the 0, the axis, if you will, of the wave. So the nodes in the s orbitals are analogous exactly to this vision, this image of a wave in a rope. All right, so we're looking at these orbitals again. So the L equals 0 gives us s orbitals. 1s, 2s, 3s, progressively larger. Ls equals 1 gives us p orbitals with 3 different orientations. They do not occur until you get to this second shell, and that's an important thing to remember. The first shell equals n equals 1 is the first shell, and only one orbital type. And when you get to n equals 2, the second shell, then you will have 2 orbital types. And they're going to be preceded by the number 2 to designate that they're occurring in that shell. So let's think some more about those orbitals and their shapes, and the lobes and the nodes. I've described them a little bit, but let's keep talking a little bit longer. Each p orbital has 2 lobes. It's like a pinched balloon is my favorite analogy, a long skinny balloon that's been twisted in the middle. And in the middle is a nodal plane that passes through the nucleus. In other words, the electrons are not in the nucleus. So the nodal plane is going to be in different orientations for each of the p orbitals, subshells. And so they're either going to be along the YZ axis. The plane of the nodal plane is on the YZ axis if it's p sub x. For p sub y, the nodal plane is going to be on the x and z axis, that plane. And for p sub z, apparently, if you follow the diagram and you follow the pattern here, the nodal plane is between on the x and y, between the x and y axes. So there's different signs correlating to the phases of a wave, representing that would represent each of the lobes of these p orbitals. All right, so there's two lobes, and there's a nodal plane in the middle where those electrons don't occur. Now, if you get to L equals 2, when you keep going on your quantum numbers, that only occurs when you have the third shell. So when n equals 3 is the first time you can encounter the angular quantum number of 2, there will be 3 subshells, and that's when you first encounter d orbitals in the subshell types. And of course, they've got 5 different interesting geometric shapes about which we will memorize very little, recognizing that they are neither the same as S nor P, and that 4 out of 5 are very similar, but trying to remember more details on that would not be within the scope of this course. If you go to L equals 3, the angular quantum number, that only occurs when you're in the fourth shell, and only then do we come to the fourth subshell type. Fourth subshell only occurs in the fourth shell, and that fourth subshell type is going to be the f orbitals. Are we showing diagrams of them? No, not going to be concerned with that. That's way beyond the concerns of this course. So we'll let that ride for somebody else's concerns. All right, so here's some more diagrams that represent the d and f orbitals in the last diagram. Do we need to have these memorized? No, but notice that there's two colors representing the positive and negative amplitudes, if you will, in the waves, but we're not going to be very focused on the details here at all. Let them go by as pretty pictures for now. Okay, so there's another aspect of understanding quantum numbers, because there is a fourth quantum number, which we haven't used so far. And that fourth quantum number relates to this concept we call the Pauli exclusion principle and electron spin. Electrons are going to have spin because that's the nature of these things. It gives rise to a tiny magnetic field and a corresponding spin quantum number. So the last quantum number of the set of 4 becomes the spin quantum number, so it's m sub s. Pauli was a scientist whose name gets attached to this concept, who came up with this idea that electrons in an atom there's never going to be 2 that have the exact same set of quantum numbers, because they're always going to be, they may be similar, but they're going to be having something opposite. No 2 electrons will ever have the same 4 quantum numbers. In other words, each electron has a unique address. It's like being in a huge sports stadium, and you got to find the right level, the right section, the right row, and the right seat. Each of those descriptors will be unique for your seat in a sports stadium. Same kind of thing with an electron. You're going to have unique values for n and L and m sub L and m sub S. Each electron will have unique values, and so each orbital that's described by m sub L has 2 possible values of m sub F, m sub S. And that results in the notion that each orbital holds at most and only 2 electrons. So what are those values for m sub S? The values for m sub S are different from the rest because they're no longer integers, but we'll come back to that. So the evidence for this is in part reflected in these closely spaced pairs of lines that were observed for the sodium line spectrum. There are 2 electrons with closely related energy levels for transitions that give this wavelength of emitted light. And I pointed this out earlier, I believe. And so if you were astute to see that there were 2 lines there closely spaced because of their energetic similarity. They're very energetically close as well. So where does that come from? It's that last quantum number. And those last quantum numbers are going to be plus and minus 1/2. But keep going. We're going to look at this in another sense with this diagram for a minute. This quantum mechanical model for atomic, and that correlates to atomic line spectra, has to do with the idea that there are only certain allowed transitions between energy levels for electrons for any specific atom. And so the different so from when an electron falls from a higher energy outer shell orbital to a lower energy inner shell orbital, some kind of electromagnetic energy with a specific frequency corresponding to the energy difference of the orbitals will be observed. So it could go in various ways, from ultraviolet range of transitions to infrared range of transitions, and some of them are going to be in the visible range. Those are the ones we'll most often see. No kidding, unless you've got special detectors. And so there's possibilities of their going from 6th, 5th, 4th, 3rd, and 2nd shells back down to a first shell or a lower shell. And so each of these spectral lines that you see in atomic spectra corresponds to electronic transitions from outer shells to inner shells. Certain things with certain energy transitions will be characteristic for every element. There are names for these, like the Balmer series. The Balmer series correlates to a particular type of calculation in a moment that we'll talk about briefly, but you won't be asked to do that kind of calculation. And so where they come from is which shell, how that calculation derives has to do with which shell an excited electron started from before it returns down to some lower energy level. So these UV ones are going back down to shell number 1, the first shell, the UV ones. The infrared ones are quite a different thing. They're going to come back down to a 3rd shell. And the ones in between, apparently, in this diagram are the ones that are going down to the 2nd shell. And so they're coming from some higher energy down to the 2nd shell. This energy transitions can be calculated, interestingly enough, and how physicists came up with this is not for us to understand, but here's what it looks like. I'm going to show you an equation briefly. Don't worry, you won't have to calculate one. So the shell is between the transition of the electron from an outer shell to a more inner shell can have its energy related to its wavelength and frequency, of course, and the shell that it begins from is going to be given one letter, namely N here, and the one it transitions to is another letter, in this case M. So it goes from larger one to a smaller one, and if N is super large, that's how you can calculate the energy of the transition for an electron that's totally removed from the atom. Interesting. So it allows for us to understand what we call ionization energy. Ionization energy and how it can be calculated for a particular element. Now, are you going to have to do this? Surely not. Now, notice that it uses what? It uses the shell transition, or the reciprocal of the square of the shells from and to, but it uses a constant. And that mathematical constant gives us a way to get to that thing. Thank you, physicists, but we won't have to use those directly. Okay, enough said on these concepts. It's just an interesting perspective on understanding how all those electron shells and shapes and orbitals correlate to actual physical evidence of emitted light spectrum.